All right, so today we're going to start chapter 7. And just as a reminder, we will not be covering chapter 6, which is a discussion about differential equations. And that's not normally covered in Calc 1. In fact, you'll see that you'll probably have a separate course in just differential equations if you are a math major. It's a great class, though. You should take it, but I don't think we can justify spending the time here with it. We're going to use or cover the last two chapters here, which are 7 and 8. Now, 7 is a set of applications for integration, and they're pretty much all physics applications. So we're not going to spend a whole lot of time with them because unless you're a physics major, I don't think it's as important as chapter 8, where we really get to learn a lot of very important integration techniques that you'll need throughout the rest of your math career. So we'll do 7 today, and then there won't be any homeworks based on chapter 7, and it will also not show up in the final exam. So it's one of those things where you should have seen it, but you will not be tested on it. Okay, now when we get to 8, we'll be learning some incredibly important integration techniques. But I do want to point out that chapter 8 is where more or less Calc 1 pretty much traditionally ends and Calc 2 begins. So some of that material that we're about to do in chapter 8, or at least in our next session, you'll almost certainly see it again when you get to Calc 2. So in a way, it's just sort of like a preview of what's coming. But it's awfully, awfully important to get to learn as much as you can about integration now because it's such a complicated thing to do. So right now, let's focus our attention on chapter 7, which again is applications. And pretty much what we're doing is we're looking to find areas and volumes of solids. So, like I said, it's really very physics intense, but it's also helpful to see more ways in which integration can be used. So we'll start with 7a, and just a quick reminder that when we're integrating, what we're actually doing is calculating the area under a curve. Like here, for example, y is f of x. We have the function, and we're integrating it between a and b. So what we're actually doing is coming up with the area of that shaded region between a and b, and also between the curve and the horizontal axis. Now, we've already seen how to do this. What we're actually calculating is a definite integral over the range from a to b. Now, we're going to extend that a little bit to more complicated cases. For example, what if instead of looking at the area between f of x and the horizontal axis, we're instead looking at the difference between two functions? Like here, you can see there's f of x and g of x, and they're both curves. So in that diagram there, you can see it's the blue region that we're really after. So the strategy here is to use the technique we just learned to solve for areas under the curve down to the horizontal axis. So we'll calculate that area from f of x down to the horizontal axis first, and then from that we'll subtract the area from g of x down to the horizontal axis. And so the difference between those two will be the area that we need, which in this case is the blue area. Okay, so that's how we're extending this technique to give us the ability to calculate areas between other types of functions. All right, so this is just to summarize it, this is what we're trying to accomplish. Now, by the way, what we're about to do only works if one function is always above the other, okay, over the interval of interest. In this case, you can see between a and b, f of x is always greater than g of x. If that's not true, we have to do something a little bit different. But if it is, then all we have to do is calculate the integral of the differences between the two functions. Okay. By the way, this is what we've been doing all along anyway. It just wasn't, that obvious because g of x in that case, when we're doing this approach, g of x is just 0. So that's why this technique and this technique are actually the same thing. It's just that we weren't aware of it before because we didn't realize that all we're really doing is looking at the area between two different functions. Okay, so what you're seeing here is an extension of what we were doing in a previous chapter. All right, now let's try an example. By the way, just like when we originally learned how to do integration, once again, all we're really doing is creating a series of rectangles, and the area of those rectangles is going to give us the area between the two curves, at least in the limit. Okay, so you can see here we've got in this diagram, we're using the left endpoint method. And you know, because the rectangle touches both curves exactly at the left endpoint. On the right endpoint, down here, it's a little bit below g of x, and up here, it's a little bit above f of x. So we'll call this endpoint xi with a little asterisk. And so what we're trying to do is find the area of this rectangle, which of course is base times height. Well, the height is the difference between f of xi star and g of xi star. The base is, we're going to just simply define it as delta x. It's some constant, and it could be anything. And so you recall, when we add up the areas of these rectangles, they will give us an approximate area that is equal to roughly what we're looking for. But it's only when we take the limit as these delta x's go to 0 that we'll end up with the correct area. Okay, so the area of the rectangles. Now this, if you notice, this is area is this blue shaded region. And if you notice, this is only approximately, remember, this symbol is approximately equal to and because what we're doing here is we're adding up a finite number of rectangles without taking the limit. And so that's why it's only approximately correct. Okay. In the limit, as delta x goes to 0, this will give us the area that we're looking for. And in that case, it becomes a limit. Okay, and here it is here. So in other words, you're taking the limit of these rectangles as the delta x goes to 0, and we end up with what we're looking for. So let's look at a quick example of this. So here we've got f of x is x plus 4, which is a straight line. G of x equals 3 minus x over 2, which is also a straight line, although with a different slope. And we're going to analyze their area between the two of them over the interval from 1 to 4. So this is what it looks like. It looks pretty straightforward. And what's interesting about this case is that if you wanted to, you could double check your results by calculating the area of a trapezoid, because you can see that's exactly what we have here. Since these are both straight lines, we do in fact have a trapezoid. But let's just use our integration skills to do this instead. So keep in mind here, f of x is everywhere above g of x, at least in the interval of interest, which is 1 to 4. Okay, so we don't have to worry about crossovers or anything like that. So what we're going to end up with is this. The area will be the integral from 1 to 4 of f of x minus g of x dx. Okay, so now it's just a question of correctly setting up this problem by substituting the functions, solving for the difference, and then integrating from 1 to 4. So this is f of x. This is g of x. So of course we have to be careful with the negative here. Make sure you've got -3 and positive x over 2. And then when you combine all these terms, you'll see that the x and the x over 2 adds up to 3x over 2, and these two add up to 1. Okay, so now we can easily solve for this integral with the power rule. Actually, what we could do is maybe factor out that 3/2. Sometimes that makes things a little bit easier for us. So why don't we try that? Let's factor out that 3/2. So this is what we're actually after right here. And of course, the integral of x dx is simply x squared over 2. Now, in this case, it's a definite integral, so we don't need the constant. And the integral of x, of dx rather, is simply x. Okay. If it's a definite integral, we don't need the constant. So here's what we end up with. 3/2 times x squared over 2, evaluated from 1 to 4. And then, so that would be the result of integrating that first term. The second term is the integral of x, or we evaluate x from 1 to 4. Now, how do we do that, by the way? Oh, by the way, not that this is absolutely necessary. You see what's happened here? This 2 was factored out to rewrite this as 3/4. I don't know how important that really is. I just wanted to point that out in case you didn't notice that it suddenly became 3/4. I factored the 1/2 out of the brackets to bring that outside. Sometimes it helps, sometimes it doesn't. But anyway, what that means is the evaluation is a little simpler because all we have to do for the first one, we have 4 squared minus 1 squared. This is what we mean by f of 4 and f of 1. And then for the second one, it's even simpler. It's simply 4 minus 1. Anyway, so when you do all the algebra, you'll see that you end up with 3/4 of 16 minus 1 plus 3. So you end up with 45 over 4 plus 3. Now, of course, we need a common denominator. Which will be 4. And our final result is 57/4. So that wasn't too painful. It's just a question of setting it up correctly. And also, of course, keep in mind that in this case, we did not have any overlap between the two functions. F of x is always above g of x, at least within the area of interest, because you see they do cross eventually, but that doesn't matter because we're only focused on the area between 1 and 4. So that raises an interesting question. What happens if they do intersect in our interval of interest? Good question. Well, here's what we have to do now. Let's say, like right here, look at this one down here that I've drawn. What if this function, whatever this thing is, you've got f of x and g of x. G of x is the dotted line, by the way. And you can see that between 0 and 2, f of x is on top. And between 2 and 3, g of x is on top. Now what do we do? Well, now we need 2 different integrals. Okay, so we're going to call, let's say this is a1 and this is a2. This is a1 right here. You can see between 0 and 2, f of x is on top, so we subtract g of x from f of x. In the bottom here, we have second area, which is a2. And between 2 and 3, we have to reverse the order of the subtraction. G of x is now on top of f of x. Okay, so that's how we handle a situation where one function is not always on top of another. What we have to do is find all the points where they cross, and we need one integral rather for each of the areas that are surrounded by them. Which means that unfortunately we do have to solve for ourselves all the points where they cross each other. But once you get that straight, and also it helps a lot if you have the graph, you have to be able to visualize which is on top and which is on the bottom. All right, so let's look at a simple case of this. All right, let's try this one. F of x is x squared, which is a parabola. G of x is 2 minus x, which is a downward sloping straight line over the interval from 0 to 2. All right, so this shaded region is what we're after. Now, if you notice, between 0 and 1, blue is on top of orange, and between 1 and 2, it's the other way around. Okay, so think of this as A1, and think of this as A2. What we're after is the sum of these two. A1 will be this one. Actually, it doesn't matter which is A1 and which is A2. This one is, oh no, sorry, this is A1. I thought I had them out of order. Because in this interval, oh, sorry, no, I was right the first time. They are backwards. This one is A2. You can see why, because wait a minute. Oh, no, I'm sorry. Blue is g of x. I keep getting the two colors backwards. So see, in this range, all right, hold on. This helps. All right, this will help. And then here, f of x is above. There we go. Now, it turns out this is A1. Okay, great. And this is A2. All right, now we got that straight. So we just have to calculate them individually and then add them up. Okay, so A1 is the range from 0 to 1, where g of x is on top because that's the blue line. And then from 1 to 2, it's the other way around. Okay, now it's all set. All right, so quick reminder. Let me just write these in here again. Oh, they're over here. F of x is the curve, g of x is the straight line. So for A1, we have the difference between g of x rather, and f of x because g of x is on top. The integral is going to be taken over the range from 0 to 1. And so remember, g of x is 2 minus x. And here we subtract x squared. So this is where we're actually integrating. And you can see that we can break this up into 3 separate terms and evaluate each one using the power rule. Okay, so for example, the integral of 2 dx is 2x. The integral of minus x is minus x squared over 2. And then the integral of minus x squared is minus x cubed over 3. Okay, now here this is a definite integral. We don't need the constants. Okay, so for example, here's the 2x minus x squared over 2 minus x cubed over 3. We have to evaluate these over the interval from 0 to 1 because that's the range within which g of x is on top. All right, well, that's pretty straightforward. So in other words, all of this is what we would call f of 1. This is f of 0. So you're replacing in the first case all the x's with 1s, in the second case with all 0s, and ultimately this reduces to 7/6. Okay. So that's A1. A1 is equal to 7/6. Then what about A2? Now remember, this is the range between 1 and 2, the red area, where all of a sudden this time f of x is on top. So remember that f of x is x squared and g of x is x minus 2. So here we have f of x, and from that, oh, sorry, that was, I copied wrong. This is 2 minus x. Okay. Oh, now, of course, once you distribute the negative sign over these two terms, we end up with x squared minus 2 plus x. And again, using the power rule, we end up with the integral of x cubed over 3. Rather, the first term becomes x cubed over 3. The second term is negative 2x. And the third term is x squared over 2, again, based on the power rule. And now we'll integrate or evaluate this from 1 to 2. Okay, let's see how that works out. So this is f of 2. This is f of 1. And if you go through all that algebra, you'll see that this ends up being 11 over 6. So if you look at that graph we had back here, that black shaded region is equal to 7/6. And the red region is 11 over 6. Okay. So that means they add up to 18 over 6, which is, of course, just 3. And that's it. And we're done. Okay, so because they crossed, we had to do 2 integrals instead of 1, but it's the same basic setup. And also, yeah, I just realized I don't think we demonstrated where they cross each other. All right, well, how is that done? Let's sneak that into here. F of x is x squared. G of x is 2 minus x. So how do you know where they cross? All right, well, you set them equal to each other. So you've got x squared equals 2 minus x, x squared plus x minus 2 equals 0. So this one can be solved with a quadratic equation, or else you can factor it. So I'm just going to quickly factor it. And that means that x plus 2 equals 0, x minus 1 equals 0. Okay, so what this is telling me is that the two functions will cross when x equals -2 and +1. So here's the +1, and we already have that. So we already knew that between 0 and 1, g of x is on top. Between 1 and 2, f of x is on top. What about that -2, though? Well, it turns out, let's say we extend these. It's true that they cross here, but our interval of interest is only 0 to 1. So that crossing point doesn't make any difference to our problem. Okay, we can basically ignore it. It's only the crossovers in the area that we're interested in that really matter. So there's only one, and that happens at x equals 1. So that's why we integrated between 0 and 1 and 1 to 2. All right, so now here's something that might surprise you. This is something we haven't done before. What if instead of looking for areas underneath these two functions with respect to the horizontal axis, what if instead we need areas between these functions and the vertical axis? Is it possible to use these techniques to find this area? Like, for example, here, we've already solved for this black shaded region between 0 and 2. What if that's not what I wanted? What if I want the red area? What do I do now? Well, it turns out we can integrate with respect to the y instead of x and use the same technique, except instead of looking at functions from top to bottom, we're looking at them from right to left. But that does mean we have to use y as the variable in our integration. Now, it sounds complicated, but it really isn't, as long as the functions aren't too messy. What do we do here? So we're going to change everything to y's. We're going to integrate with respect to y. We're going to have two functions, and the interval of interest will also be different, by the way. Okay, in other words, instead of 0 to 2, we'll have whatever this is up here down to 0. So we have to find these first, and then we can go ahead and integrate the normal way. So what do we do? Well, we know that f of x is x squared. We know that g of x is 2 minus x. But let's say this red area is what we're after, okay? Not the blue this time, but the red. So we have to imagine looking from right to left, and that means we have to define one of these functions as the, quote, right function, and the other one as the left function. Instead of top and bottom, we have right and left. So first we have to rewrite these in terms of y. Okay, so in other words, if y equals x squared, that implies that x equals radical y. And if g of x is 2 minus x, that implies that x equals 2 minus y. And then furthermore, we'll let the first function become v of y. And the second function, g of x, will become u of y. Okay. So, I mean, to a certain degree, it's arbitrary, which is which, but what we're after is this. If you look at that graph very carefully, and again, let me label these for you. X is the same thing. We have a v of y. Here we have u of y. So when we integrate, we're going to have u of y rather, minus v of y. And so you can see that within the area of interest, which is just this part here, the area of interest is defined with respect to the vertical axis from 0 to 1. And you notice within that area, u of y is to the right of v of y. Okay. So in other words, You look from right to left, blue is to the right of orange. So blue, which we previously were calling g of x, has now become u of y. Orange, which was previously being called f of x, is now v of y. So we're going to think of these. Let me write this a little neater. As the right function. And here we have the left function. Now, what's convenient this time around is that while with respect to top and bottom, there's a crossover point between these two functions. When you're looking from right to left, that actually does not happen. Okay, throughout the entire interval of interest from 0 up to 1, blue is everywhere to the right of orange. So we don't have to bother with any crossovers. We can just go ahead and integrate directly the way we did before. So what we do need to do is make sure that we know what the interval of interest is, though. And so we know that we're starting with 0. The question is, how do we know that it goes only up to 1? Well, again, we previously did this. We showed that when we factor the 2 cross, where x equals -2, which we don't need for this one because that's not the area of interest, but we do know that x equals 1. And so when x equals 1, if you notice, that's when we reach the height of this area of interest. And by the way, we're now calling this C and D instead of A and B. And so G of 1 is equal to 1. And so is F of 1. In other words, so that's how we know that the interval of interest is from 0 up to 1. Okay, because that's where the two functions cross. So anyway, so that's what we're after. So now that with all this setup, we're going to actually go ahead and do it. So I've written it all in terms of y now. So once again, we always think in terms of right and left. U is right. D is left. We've already solved for these in terms of y. So u is 2 minus y. And then from that, we subtract radical y. Now, because we're integrating with respect to y, the rules haven't changed. It's just the variable of interest is y instead of x. We're still using the power rule here. So in other words, here it is. We're going to break it up into 3 separate integrals. We have 2 dy minus y dy minus radical y dy. And just keep in mind that radical y is y to the 1/2 power. So based on the power rule, this is y squared over 2, and this is y to the 3/2 power over 3/2, which we simplify here, which we should do. And so if you notice, the constants are getting factored out. Here we move that -1/2 to the outside. Same thing here with this 2/3 dividing by 3/2 is the same as multiplying by 2/3. That's where this is coming from. Now we're ready to go. Actually, let me copy this here so you can see it better on this page. All right, so here now, remember, there's a constant here, and then within the parentheses or brackets, we'll have 1 minus 0. Here we have the -1/2. Within the brackets, we have 1 squared minus 0 squared. And then here we have the -2/3. And within the brackets, we have 1 to the 2/3 minus 0 to the 3/2 rather, sorry. And then you can see algebraically, ultimately, when you go through all the steps, you'll see that you end up with 5/6. Okay, so really the only thing that changed was that you have to rewrite the functions in terms of y and then redefine the interval of interest. Once that's done, the rest is exactly the same. You're taking definite integrals of the differences and then solving. All right, now that's going to come in handy in the next section, which is 7b. Because, some of these solids that we're trying to generate, we can best do it by going from left to right, some of them from top to bottom. So let's see what that's all about. All right, so we're going to try to look at some basic forms that you've seen before: spheres, cones, and pyramids. These are all three-dimensional objects. And so in order to generate them, we need to rotate a basic two-dimensional shape like a rectangle around one of the axes. A quick reminder, in case you've forgotten, I don't think anybody has this memorized after all these years. Maybe you do. The volume of a sphere, 4/3 pi r cubed. If you still remember this, you have an excellent memory. Volume of a cone, 1/3 pi r squared h. Volume of a pyramid, 1/3 AH, where A is the area of the base, which is typically just a rectangle. Now we're going to think in terms of a cross section here. In other words, like here, look at this shape. Well, it looks like an airplane hangar. And but the thing is, that plane is what we're interested in because it slices through, and we can use that plane to come up with the area that we need. From a two-dimensional perspective, we would just be seeing the semicircle. So what we're going to basically do is create the volume of the solid as the sum of an infinite number of these semicircles using integration. Now look at this one. Oh my God. Now this one is essentially a series of trapezoids, okay, starting from smaller to larger, and it generates this very interesting looking solid, but the cross sections themselves are all trapezoids. So the volume is approximately, now you notice how here this is approximately, if we take the areas of these slices or trapezoids and add them up, we'll get the approximate area volume of the solid. It's not until we take the limit as delta x goes to 0 that we'll get the exact volume. There it is. Okay, great. So it's the same as what we were doing a little earlier. So we called this the slicing method for obvious reasons. And of course, in each case, we have to have a basic shape to act as our slice. Sometimes it's a trapezoid, sometimes it's a rectangle, sometimes it's a semicircle. It depends on the case. So let's look at the pyramid. Oh my God, now look at this. So we're going to slice it up and come up with the volume of a pyramid. So there's the two-dimensional graph shows that there are two triangles. The big one is here. The little one is here. So the logic here is that these are what we call similar triangles, meaning that they have all the same angles, which means that the proportions of the height to the base in each one is the same. Okay, so in other words, the height relative to the base is the same for that smaller triangle as it would be for the larger triangle. So the angles are the same in both triangles. So that implies that x over s, which is the height to the width, or the base. I guess we should call it the base because it is a pyramid that we're using here. So anyway, the bottom line is that x over s, the small triangle, is equal to h over a for the large triangle. Or of course, you can rearrange it algebraically. S therefore equals ax over h. And so we're assuming that the small triangle has a square base. So therefore, when you integrate the area using the slicing method, you're going to end up with a squared x squared, where h squared is your integral dx. Well, the h and the a are constants, by the way. So we're just factoring them out, and we're integrating across h because h is the base of the larger triangle. So what you're basically doing is creating a series of these bases or slices, and an infinite number of them are being used to create this structure. And so that's why we have to take the integral. Okay, so this part is straightforward because x cubed squared is going to be, when it is integrated according to the power rule, we'll just end up with x cubed over 3. And now this time we're going from 0 to h. We haven't specified what h is just yet. And we also don't know what a is. But once we do, we can calculate the volume of any pyramid. Okay, so now, so like I said, these are I'm not quite sure what discipline would find this useful. I'm sure physics, maybe architecture. I'm not so sure. There was a time when computer graphics were all completely mathematical. People who did this had to actually do all the math themselves. You didn't have Adobe Photoshop, for example, to do all the work for you, um, or at least the calculations. So computer graphic designers would have had to be very interested or very on top of this. But anyway, what about solids of revolution? So here, what you have to visualize is that we're taking some basic two-dimensional shape and rotating it around either the vertical or the horizontal axis. Like this one, if you imagine rotating it, it's hard for me to draw it properly, but the result would be this surface on the bottom. And that, oh, I see. Okay, no, then we're not done yet because then that gets rolled over the horizontal axis to produce this thing. I'm not sure if there's even a name for this shape, but you can see we can use the slicing method to figure out its volume. Let's see. Let's take this one, for example. Now, earlier we did problems just like this. If I just wanted to know the area under this curve, it would be a simple matter of integrating this function, right? I would use the power rule to come up with x cubed over 3 minus 4x squared over 2 plus 5x. And I would integrate it from 1 to 4. And I would have 1 cubed over 3 minus 4 times. Oh, no, I start with the 4s. What am I doing? Well, anyway, you would end up with some constant result, and you'd be done. But now we're trying to rotate it around looks like we're going to rotate it around the horizontal axis, and we end up with this thing. And again, there's probably a proper name for this. I just don't know what it is. So the cross sections are circles now. Okay, these are the slices that we'll be using. And so the area of a circle is, of course, 1/2 pi r squared. I'm sorry, it's pi r squared. And this function, the radius is the height of this function at the point 4. Okay, so the radius is replaced with this function. And we'll integrate this from a to b, whatever that happens to be, whatever area we're interested in. And when you're finally done with all the power rule and actually evaluating it from 1 to 4, it turns out that we end up with 78 pi over 5. All right, now what we've just been doing is known as the disk method. Okay, so in general, what we're going to end up with is this result. Okay, and you can see why, because we had here pi times r squared. It's the r squared that came from the solid, or the this slice that we were using. So in general, this is what we'll end up with. This can be applied to a large number of different shapes. And we can also go from left to right, as we've already discussed. We can rotate around the vertical axis, and then we replace the limits of the area of interest is now C to D. And instead of f of x, we have g of y, dy, like this one. So here's a graph of what this looks like. Oh, now that's interesting. So we create our disk, and we rotate it, and we end up with this. Oh, I'm not sure what I'd call that, but a solid of revolution. And if we're only interested in the area from 0 to 4, we replace g of y with radical 4 minus y. That's the function that bounds the curve. And then again, the rest is just going ahead and calculating a traditional definite integral from 0 to 4 in terms of y, that is, though. And, when you go through all the steps, you'll see that ultimately you end up with 8 pi. All right. Oh boy. Now, we're getting into some deeper territory. Volumes with cylindrical shells. Oh my God. Now look at this. What do we do now? So we're actually doing both this disk method to get the revolution around the x-axis, and then we're going to use the so-called shell method to revolve it around the y-axis. Okay, so in other words, from around the x-axis is known as disk, around the y-axis is known as shell. Now look at this thing. So there's 2 pi. Now, let's see. Oh, wait a minute. Because it's a cylinder. Okay, we didn't specifically remind ourselves what the formula is, the volume of the cylinder, but we do need 2 pi x f of x because it's a cylinder. Let's look at this example. We go from, this is the function 1 over x, and we're going to rotate it. We're only interested in the area from x equals 1 to 3. And this is the final result. So the function is very simply 1 over x. And we're only interested in the area from 1 to 3. And so we always have the 2 pi x when we're creating a cylindrical shape, I guess you should call it. And then we fill in the function itself. And this could have been any function we chose. It could have been, for example, x squared or something like that. But whatever that function is, we multiply it by 2 pi x, and then we do the definite integral. And in this case, we ended up with 4 pi. All right. Now, by the way, pi is a constant. You don't be confused about that. So here I had 2 pi dx. This is a constant. I moved it outside. And of course, the integral of dx is just x plus c if it's an indefinite integral. So I ended up here with 2 pi x evaluated from 1 to 3. Okay. So here's f of 3 minus f of 1. So I'll ultimately end up with 4 pi. All right. And now shell. You can always use either disk or shell or some combination of both. With shell, we're using the vertical axis, and you can see we have the function g of y is 2 over radical y. The original function was y equals x squared. So once again, now it's the same thing. We have 2 pi, except instead of 2 pi, from A to B, before we had this. And so shell tells us to do this. We're now rotating the other direction. Actually, I should call it G of Y. Otherwise, it looks like it's the same function. I'll move it down here. And of course, you can move the 2 pi to the outside if you want to, just to simplify the integration. And so in this case, we ended up with 256 over 5 pi. So anyway, those are the basic techniques um, for finding the volume of a solid. Um, and then again, this is a traditional topic in calculus textbooks because calculus was originally designed to explain physics applications. But I mean, if you need this in whatever you're studying, that's fine. But so, like I was saying, we're not going to do any assignments based on this, and we're not going to have it as part of the final exam. But it is good that you've seen it at least once. So if you encounter it again in Calc 2 or 3, you'll at least know what it's all about. All right, so the next time we meet, we're going to go into 8, and then from then on, we're just going to spend all of our time learning many, many important integration techniques, and there's so many of them. It's a huge. I mean, you could write a whole book about integration. I mean, there's so many to choose from. We're going to learn 4 very important ones that will help us when the other techniques we've learned are not going to work. And of course, like I said, part of the challenge there is identifying which ones we need to use and when, because like I said, there's so many, and sometimes it's very hard to see the differences between the different cases. It's awfully subtle. So we need practice identifying which problems we should be using for which cases. So anyway, so we'll do that next time. And so, like I said, this is it for our discussion about chapter 7. So from now on, it's all about chapter 8. So I'll see you next time.